Please let me know when I should start. Hello, hello. Shall I start, sir?
Hello everybody. This is a great pleasure to listen to Pranjal Talukdar, who will be presenting joint work with Indy Barua on the least R gaps in partitions and identities for the Rogers Townsend continued fraction. Go ahead, Pranjal.
Thank you, sir. Thank you for the invitation, for giving me this chance to talk about my research. So the title of today's talk is on the Lister gaps in partitions and identities for the Rogers-Ramanujan continued fraction. So the title of this talk has been taken from two chapters of my PhD thesis, which has been recently completed under the supervision of Professor Noyani Dekaburwa. So the contents of today's presentation is so first we will look at some preliminaries and then we will go to the main topics of today's talk. Okay. So we start with this standard Q product AQN for complex numbers A and Q with mode of Q less than 1, and this AQ infinity is the limiting case of it. Okay. Also, for our convenience, we take Fn to be Qn infinity. Next, we recall the definition of Ramanujan's general theta function, which is given by this infinite series, and which can also be represented as this product, this infinite products. Okay. And this last equality is famously known as the Jacobi's triple product identity. We now mention three special cases of f of AB, which will be vital in today's talk. So first one is phi of Q, which is basically A and B replaced by Q. Then next is psi Q, A replaced by Q and B replaced by Q cube. And the last one is f of minus Q. We also define the chi Q to be this infinite product. Next, the well-known Rogers-Ramanujan continued fraction is defined by this continued fraction, and the associated Rogers-Ramanujan functions are denoted by these two infinite sums. Okay, so Rogers, in his seminal paper in 1894, he proved these two infinite sum to infinite product identities for these two Rogers-Ramanujan functions, ZQ and HQ. Okay, and these two identities later became famous as the Rogers-Ramanujan identities. He also proved that this continued fraction has a connection with these two functions, that it can be expressed as a quotient of these two functions with an additional factor of q to the power 1 by 5. So for our convenience, we take this fraction as RQ. Okay, so we will use this notation or also this notation wherever it needs. Okay. So when the definition of partition of a positive integer, which is a finite non-increasing sequence of positive integer parts, which adds up to n. And the number of partitions is denoted by Pn. So for example, for n equal to 4, it has 5 partitions, which are this 4, 3, 1, 2, 2, 2, 1, 1, and this one. Okay, so P of 4 is 5. And the generating function of partitions was given by Euler in long back 18th century, which is given by this 1 by QQ infinity. Okay. Ramanujan, in his groundbreaking work in partition congruences, proved these three partitions, modulo 5, 7, and 11 in 1999. He also conjectured more general congruences for Pn modulo arbitrary powers of 5, 7, 11. So this actually set the grounds for the future mathematicians to look for other arithmetic properties and other arithmetic aspects of the partition function, as well as the other restricted partition functions. Next, we move to the first topic of today's talk, which is the least star gaps in partitions. So, the concept of max in a partition was first introduced by Andrews and Newman in 2019. Okay. So, the max of a partition is the smallest positive integer which is missing from that partition. So, for example, max of this partition 4 is 1. Max of this partition 3,1 is 2, because 1 is present here and 2 is the smallest part which is not present here. And max of this partition is 3. They also studied another concept called minimal odd excludent, which is nothing but almost similar, but here they consider the smallest odd positive integer missing from that partition. Okay. So, for example, minimal odd excludent of 4 is 1, minimal odd excludent of 3,1 is 5, and minimal odd excludent of 2,1,1 is 3. Okay. If you observe that this partition here max is 2, because the least positive integer which is missing from this partition is 2, but the least odd positive integer which is missing from this partition is 5. Okay. So they studied the arithmetic properties of some max related functions, which they define by these three, and these two are basically this sigma max. This sums all the minimal excludents of all the partitions of n. Similarly, this one also, this sums up all minimal odd excludents of all the partitions of n. And this is a counting function. This counts the number of partitions with odd max. Okay. So Andrews and Newman, they derived these generating functions for sigma max and sigma minimal odd excludent, and they also established this relation between this counting function and sigma max modulo 2. Recently, Borua, Bhuria, Yuni, and Mazi, they refined the expression for sigma max by introducing these two functions, which are basically two counterparts of sigma max. So for this first one, they summed all the maxes which are odd, and this one they summed up all the maxes which are even. Okay, so they actually refined the summation of this sigma max, and they proved that this sigma odd max has this generating function and sigma even max has a disgenerating function. Okay, and if we add this up to, so this term and this terms gets cancelled out, and we will get the original expression due to Andrews and Newman. So there are many more works on max and max related partition functions which can be viewed in these papers. This actually includes relation of maxes with rank and crank. There are identities which relates maxes. There are max of various different restricted partitions and other arithmetic properties of max. So we are now interested in a generalization of max. So we define the least star gap of a partition to be the smallest positive integer which does not appear at least r times. Okay. So for max, it was the smallest positive integer which did not appear at all. And now we are defining something that does not appear at least r times. So the generalization here is on the number of appearances. Okay. So Ballantyne and Marca in 2020, they initiated the study of least star gaps, and they denoted the least star gap by this ZR pi, and they also studied this the summation function for all the least star gaps. Okay. So in max terminology, we can say we write that this ZR pi, we can also say at R max pi, and this can be also viewed as this sigma R max n. Okay. So for example, this one max of this partition is 5, because 5 is the least positive integer which does not appear at least one time in this partition. But 2 max is 4 because all the other parts which are less than 4, they appears at least 2 times, and 4 is the smallest part which does not appears at least 2 times. Okay. Similarly, 3 max is 2 and 4 max is 1. Okay. We also define r minimal odd excludent of pi to be the smallest odd positive integer which does not appear at least r times. So Ballantyne and Marca, they proved this generating function for sigma r max, and they also found some identities relating partition function and this summation function. Then following their work, Chakraborty and Rai, they studied arithmetic properties of sigma 2 max, sigma 3 max, modulo arbitrary powers. So in our work, we have studied these functions, sigma r max. We have also studied its even and odd counterparts. We have also studied the summation function for this r minimal odd excludent, and we have also studied this counting function. Okay. So we have derived the generating functions. So these are the generating functions for sigma r odd max, sigma r even max, sigma r minimal odd excludent, and the counting function. Okay, so the proof techniques are almost similar. So in the next 2 slides, we'll be seeing how a short proof of this identity 4. Okay. So here we So we observe that if we here we observe that if we add these 2 things, when we add these 2 things, so this and this gets cancelled out, and this half and half, so it gets f2 r square by f1 f1, and this leads us to this identity of Ballantyne and Marca. Okay, so next so in their paper, Ballantyne and Marca, they proved this result using some identities. Okay, so in our work, we will be giving a alternating proof of this generating function, which can be also applied to find these generating function. Okay, so this is actually this is not one. This should have been this one. Okay, so we will be now seeing a proof of this generating function. Okay, we now want the summation sigma r max n, and we want it to be equal to be this one. So for this, first we define that P r max m comma n, this counts the number of partitions of n such that r max pi is m. Okay, so we denote the number of partitions of n such that the least star gap is m by this P r max m comma n. Okay, and then we construct this double series. Okay, so here m where n is from 0 to infinity, since the number being partitioned cannot be negative, and m starts from 1 to infinity because since r max is a positive integer. Okay, and here if you notice that the exponent of z, this is the least star gap or r max, which so the exponent of z takes care of the r max, and the exponent of q, this takes care of the number being partitioned. Okay, so yeah, now we want to simplify this and have a nice formula for this. Okay, so we keep z to the power m as it is, and now we want to see that what happens to this p r max m comma n q to the power n, and n is from 0 to infinity. Okay, so first of all, we know that the generating function of partitions, so this basically the generating function of partition is basically 1 by 1 minus q to the power n equal to 1 from infinity. Okay, but in that generating function, there will be also some parts involving n, which will be occurring r times or r plus 1 times, because then in below there will be some terms like 1 minus q to the power m, and it will be it will in turn it will give rise to 1 plus q to the power m, or in on all these parts it will generate all the parts that m appears. Okay, so first we restrict here that n cannot be m. Okay, and now we proceed to see this how this restriction this works. Okay, so since this denotes the number of partitions where least star gap is m, so the least star gap is m, this means that the parts which are less than m, they should appear at least r times, because m is the smallest part which does not appear at least r times. So each of these partitions, the parts which are smaller than m, they should appear at least r times. So this factor should be there in each of these partitions. Okay, and what are the chances of occurrences of m? So in these partitions, m may occur or m may not occur, but m can occur at least r at max r minus 1 times. Okay, so based on the occurrences of m, this product term comes. Okay, so now we have this double sum is simplified into this single sum. Okay, this takes care of all the parts. Takes care of these two, takes care of the fact that m is the least r gap. Okay, so now if we allow this n to be equal to m, that means if we multiply and divide by q 1 minus q to the power m, then this becomes 1 by q infinity. Then it comes outside the summation. Then this term comes here, and if we sum this up, this will give us this one, and with these two products it will simplifies to this one. Okay, so these are a double sum which involves the number of partitions of n which with least star gap m. Okay, but we want the summation, we want the summation of all least star gaps. So if there are this number of partitions with least star gaps m, so what is the expected sum of all the least star gaps? Because this many number of partitions having this least star gap m, so the summation of all least star gaps will be m into this p r max m comma n. Okay, so if we want to obtain a suitable expression for the summation of least star gaps for this double sum, what we expect? We expect this m somehow to come here. Okay, we expect this m somehow to come here, and we actually then we do not require this z anymore. Then and we also means wish to this z to vanish. Okay, so what we do, this is actually a standard trick. This is actually have been done in the previous papers related with max. And so what we do, we basically do we basically differentiate m this double sum partially with respect to z, and then put z equal to 1. So this then if we differentiate this partially with respect to z, then this m comes here, it becomes z to the power m minus 1, and when we put z equal to 1, then this gives the summation of all the least star gaps of all the partitions. Okay, okay, so this gives us the generating function for the summation of all least star gaps. Okay, and what happens to the right side? So here it is, we are differentiating with respect to z, so this m comes here and this becomes z to the power m minus 1. Okay, so this is the expression after taking partial differential and putting z equal to 1. So then we multiply this, and actually we just shift the limits, and then from these two, since it is m plus 1 and this is m, so when we take the difference, this only this q to the power r m into m plus 1 by 2 remains, and this by definition of this Ramanujan theta function, phi of q, this we can write as this q to the power 2 2r infinity by qr. q3/2 are infinity, and which finally boils down to this generating function. Okay. Next, we move to some asymptotic formulas. So when given two functions fx and gx, so we call fx is asymptotic to gx as x tends to infinity if and only this ratio tends to 1 when x tends to infinity. Okay. So for Tn, sigma max, and the even and odd counterparts of sigma max, we have these asymptotic formulas due to Hardy and Ramanujan, Grebner and Knopfmacher, and recently by Borman and Singh. Okay. So motivated by these results, we have proved these two asymptotic formulas for sigma r max and sigma r minimal or excludence. Okay. So in the next few slides, we'll be giving the details of the proof of this formula. Okay. So the proof of this formula is based on a Tauberian theorem of Ingham. So where he states that if CQ is a power series with radius of convergence 1, and the coefficients, this Cn is weakly increasing, and if there are some constants mu, nu, and lambda which this condition, then the coefficients of this power series satisfies this asymptotic result as n tends to infinity. Okay, so we will be applying this theorem of Ingham to obtain an asymptotic formula for sigma r max n. Okay, yeah. So first of all, we need this assumption: Cn is weakly increasing in nature. So if we we wish to prove this lemma. We wish to prove that the sigma r max n is weakly increasing. Okay. If we can prove this, then by using Ingham's Tauberian theorem, we can obtain an asymptotic formula. Okay. So we want to show that this is weakly increasing, which means that sigma r max n is should be less than equal to sigma r max n plus 1. Okay. So we construct a map from all the partitions of n to all the partitions of n plus 1. Okay. Means the set of partitions of n to a set of partitions of n plus 1. Okay. So if pi is a partition of n and the least star gap of pi is not 1. Okay. That means what? That means the part 1 that appears at least r times. Okay. And some other parts which are bigger than 1, this is the least star gap. So if the least star gap is not 1, then what we do? Under this map, psi, we add 1 as a part to pi. Okay. So then this pi is a partition of n, and since we are adding 1, so this sigma pi, this psi of pi, this becomes a partition of n plus 1. Okay. So what is the difference? That the difference is that 1 has been added as a part to pi. Okay. And since sigma r max is not 1, so that there is no difference in the least star gap. So least star gap remains the same because it already appears more than r times. So we are just adding 1 as a part. Okay. And if the least star gap is 1, then what we do? We to construct a partition of n plus 1. So since the least star gap is 1, so 1 does not appear at least r times. Okay. So it may happen that it is appearing r minus 1 time. Okay. So if it appears r minus 1 time, and by this similar to this one, if we add 1 as a part, then this least star gap will not be 1, because then it will be this 1 will appear r times. Okay. So we will avoid this thing. So when this sigma, when this least star gap of pi is 1, then what we do? We add this 1 to the largest part of pi. Okay, so say for example, the largest part of pi is some lambda. Okay, then under this map, the largest part of this psi of pi will be lambda plus 1. Okay, and in this way, this least star gap is not harmed. Okay, least star gap remains the same. So it is actually easy to observe that by our construction that if pi 1 and pi 2 are two distinct partitions of Pn, then its images will also be distinct. Okay, which actually implies that this map is injective. Okay, and as we have discussed that Rmax remains invariant under this map, so this does not change. Okay, so from these two observations, we have this lemma that this sequence is weakly increasing. Okay. So after this weakly increasing nature, and since all these Q products are taken under the consideration that absolute value of Q is less than 1, so the radius of convergence will always be 1 or less than equal to 1. Okay. So first so now we back to the proof of asymptotic formula of the sigma max and via the theorem of Ingham. Okay. So for that one, so we now consider this power series, which basically is a generating function for the sigma max, and which is basically this Q product. Sorry for this equality sign here, double. Okay. We also recall this transformation formula for the Dedekind's eta function. Okay, so this states that 1 over e to the power minus t, e to the power minus t infinity is asymptotic to this factor whenever t tends to is positive side of 0. Okay, so when we replace q by e to the power minus t in this thing, and we take t tends to 0 plus, then from this transformation formula, this x are e to the power minus t, we simplify it, then we observe that this is actually asymptotic to 1 by 2 to the 2 root r e to the power pi square by 60. Okay, and we have already obtained that this sigma max is weakly increasing. So now we invoke Ingham's theorem. Okay, because we wish to have something like this one, and this was the assumption. So both has been satisfied. So now we use Ingham's theorem with mu equal to 2 by root r, then phi equal to 0, and lambda equal to pi square by 6 based on this thing. Okay, and then we obtain this asymptotic formula for sigma r max. Okay. There are some more arithmetic properties which have been found recently by Borua, Bhuria, Union, Mazi, and next by Burman and Singh for this sigma odd max and sigma even max. Okay, modulo 4, 8, etc. So motivated from these results, we have also proved these identities for sigma r odd max and sigma r even max for r equal to 2 or 3. So for r equal to 2, we have this identity. Okay. We have also proved some class of congruences, infinite families of congruences. Okay. So to state those congruences, first we have to recall the definition of Lucas sequence. So for integers a and b, the AB Lucas sequence is defined by this relation 13. Okay, with these two initial terms. And the rank of this AB Lucas sequence is the least positive integer k such that Sk is divisible by m. Okay, and we denote the rank of Sn by this symbol. Okay. So from if you look closely to this formula, so when we put a equal to 1 and b equal to -1, so this becomes Sn equal to Sn minus 1 plus Sn minus 2. So this is nothing but the well-known Fibonacci sequence. Okay, so our Fibonacci sequence is a Lucas sequence, which is where A is 1 and B is -1. Okay, with these initial terms, and it is from these terms it can be easily seen that this rank of this sequence modulo 2 is 3 and rank of this sequence modulo 3 is 4. Okay, so to state our next theorem, the congruences for in between the sigma are odd max and sigma are even max. First we construct these two Lucas sequences. Okay, where this gamma is defined by this q product and with this initial terms, and let this denotes the rank of this Lucas sequence Gpn modulo any positive integer n. Okay, so if Gpn and Hpn these satisfy these two Lucas sequences, then we have these infinite families of congruences for sigma to odd max and sigma to even max modulo m. Okay, and if with this we add this initial this extra condition, then we get another family of infinite congruences modulo m between sigma to odd max and sigma to even max. So we'll not go into details of these congruences because they are quite a bit long actually. Okay. Next, we move to the second topic of today's talk, which is identities for the Rogers-Ramanujan continued fraction. So Ramanujan, in his first letter to Hardy, he mentioned an elegant identity which expressed the RQ5 as which express RQ whole to the power 5 as a function of RQ5. Okay. So after seeing this identity, Hardy reacted that he was actually amazed, and he reacted that these formulas defeated him completely, and this could only be written down by a mathematician of the highest class. Okay. So after Ramanujan, the proofs of this identity were given by these various mathematicians in different ways. The special thing about this identity is that there are actually this identity is of a very rare kind. Okay, where in the left hand side we have a function of rq, and in the right hand side we have a function of rq5, and this function of rq has been expressed as a function of rq5. Okay, so in literature we actually, when we were doing this work and we actually did an extensive literature search, then we could not find actually that if there exists some other identities of this sort where a function of rq has been expressed as a function of rq5. Okay, so in our work we were able to find some analogous identities to that identity of Ramanujan. So in this equation 18, if you can see that here in the left hand side we have a function of rq4, and in the right hand side this rq4, this function we have expressed it as a function of rq5 rq20. Okay, so this is, in some sense, this is a similar or analogous to that identity of Ramanujan. In this second identity we have expressed a function of rq square rq4 as a function of rq5 rq10 rq20. In this next one, this is actually these expressions are a bit long, but in this one also, in the left hand side we have a function of rq and rq square, and in the right hand side we have all these functions of rq5 and rq10. We also have further modular identities relating rq and rq with rq2, rq3, rq4, rq7, rq11, rq19 with r of minus q, and this can be found in these papers of different mathematicians, and also in various places of Ramanujan's notebook and lost notebook. We also find, okay, wait. So in this slide, we see some examples of some modular identities due to Ramanujan. Okay, so he recorded these identities which relates RQ with various values of RQN. Okay, in various places of his notebooks and lost notebooks. We have also proved new identities which connects RQ with RQN for various values of n. So, for example, in this equation 26, we have connected RQ with RQ2, RQ3, and RQ6. Okay. And this identity is actually some kind of an elegant identity, because here we have this 1 by RQ2, RQ3, and here we have this, it's reciprocal, and same happens in this one. Okay. In this next identity, we have connected RQ with RQ2, RQ4, and RQ8 with RQ16. Next, in this next theorem, we have connected RQ, RQ square, RQ3, RQ6. Okay. Similarly, for this one, we have connected RQ, RQ3, RQ2, RQ6, RQ12. Okay. And in this one, we have connected RQ with RQ2, RQ3, RQ6, RQ12, RQ24. Okay. So for this slide, we have actually used this script RQ, because of these expressions are a bit long, so it actually doesn't covers in these slides. Okay. So next we move to the identities for the Rogers-Ramanujan functions. So towards the end of his brief article in Proceedings of London Mathematical Society, Ramanujan mentioned that he has found an algebraic relation between GQ and HQ, which is this. And he also stated that another noteworthy formula is this one. So each of these formula is a simplest of a large class. So this was his comment on these two identities, but he never revealed that how many identities were there, or what he meant by this large class. Okay. So later it was came to be known that these two identities were from a set of 40 identities for GQ and HQ that Ramanujan recorded, but he never published. The complete list was published much later by Barth, and the proofs of these 40 identities were done by these mathematicians later on. So after Ramanujan, there have been many new identities for this GQ and HQ. We have also found some new identities involving GQ, HQ, and GQ to the power n, and HQ to the power n for different values of n. So for in these two identities, we have connected GQ with GQ2, GQ3, GQ6, HQ, HQ2, HQ3, HQ6. Similarly, for this one, we have connected this ZQ, ZQ3, ZQ6, ZQ12, and the same values for HQ also. And also, these three are also some new identities of involving ZQ and HQ. So for the last part of today's talk, we want to demonstrate the proof of this identity. Okay, so this is a new identity which we discovered during our work. So for this one, so for the proof of this identity, first we set A equal to Q and B equal to Q to the power 5 in the expression of this Ramanujan's theta function. Okay, so if we put A equal to Q and B equal to Q to the power 5, then this infinite sum, this boils down to this infinite sum, which is Q to the power 3n square minus 2n. Next, we look at this power 3n square minus 2n. So it can be easily observed that this 3n square minus 2n can only be congruent to 0 or 1 or 3 modulo 5, which means that it cannot be congruent to 2 or 4 modulo 5. Okay, but since this series this contains only the powers of q of this form, so what we observe that the powers of q in this expansion cannot be of the form 5k plus 2 or 5k plus 4. Okay, and if we add if we multiply q with it, so we can say that the powers of q in the expansion of q into f of q into this f q q5 cannot be of the form of f 5k plus 3 or 5k. So this is one of the important means observation. Okay, so we have observed that the powers of q in this expansion are not of the form 5k plus 3 or 5k. Then it must be, it is obvious thing that if somehow we can, if somehow we can express this series as some, as the sum of some, as the summation of some counterparts of uh, q to the power 5 or some series containing a q to the power 5, then it it may be helpful to us. Okay, so we tried to find the 5 dissection of this series, okay, which involves functions gq and hq. So a t dissection of a power series is basically a way of expressing this power series in t minus 1 power series of q to the power t. So for example, a 5 dissection of psi q is given by this one. Okay, so here you observe that this left hand side is a power series in q, and whereas the right hand side power series is in q to the power 5. Next, we recall the Jacobi's triple product identity, and if we put a equal to q and b equal to q to the power 5, then this identity gives us these three factors, and when we multiply and divide by minus q3 q6 in infinity, then these three terms actually give us this minus q comma q square infinity, and whereas this remains as same, and this is nothing but the pi q that we defined, and this is nothing but the psi of minus q cube, which actually we defined in the previous slides. Okay, so now we have expressed this f of q comma q to the power 5 in some known functions. Okay, so now we require to find 5 dissections of this q into chi q and psi of minus q3. Okay, but we have a 5 dissection for psi of minus q3 from Ramanujan's second notebook, and if we replace q by minus q cube, then we have this identity, and we have this 5 dissection of psi of minus q3. So now we have got this 5 dissection of psi of minus q3. We only require to find this five dissections of this q into chi q, but we don't have, in the literature we don't have any 5 dissections of q into chi q. So now we go back to Ramanujan again, and from his second notebook he there noted that this phi square q and phi minus phi square q5 is equal to this 4q chi q f5 f20. Okay, so if you see this identity, then this is a power series of 5 q to the power 5. These two are power series of q to the power 5. Okay, so if we need a 5 dissections of this one, so these are already some power series of q to the power 5. The only thing remains is this one. Okay, and so what we do, we basically from this one we shift these four So we shift this f5 f20 to this side, so this becomes actually 4q chi q equal to 1 by f5 f20 phi square q minus phi square q5. Okay, then we put this 5 dissections of phi q and we get this expression. Okay, so this is now giving us a 5 dissections of 4q iq. Okay, we now simplify it again, and when we expand this square, these terms are these are the terms of after expanding the square. Okay, now let us concentrate on these three terms. Okay, so if you concentrate on these three terms, so this is phi square q to the power minus phi minus q to the power 20 minus q to the power 25 minus phi square q to the power 5, and this is 8 q to the power 5 q f of q5 q45 q15 35. Now you look at this last part of this identity. Okay, so here if we replace q by q to the power 5, so this becomes phi square q to the power 5 phi square q to the power 25. Okay, so this becomes 4 q to the power 5 q to the power 5 q to the power 45 q to the power 15 q to the power 35. Okay, so with the help of this thing, these three terms, this reduces to this single term. Okay, so now we have this all the terms here are some power series of q to the power 5, and now we have this 5 dissections of 4q iq. Okay, so to summarize all the things that we have done till now, that first what we observed, that the powers of q in the expansion of q into f of q comma q to the power 5 are not of this form 5k plus 3 or 5k plus 5k. Okay, then we express this 4q f, this one, as as an expression containing chi q and psi of minus q3. Okay, so to find a 5 dissection of this, we may find a five dissections of this one also. Then we have found some five dissections of this thing and some 5 dissections of this thing. Now we know that if we multiply these two, the powers of q, which are of the form 5k plus 3 and 5k plus 5k, are actually 0 because they are not present here. So the ultimate combination, they will give 0. So we have ultimately we have this after multiplication. So we have these five. This is the five dissections of 4q f of q comma q5. Okay, and we know that in this expression, the terms, the powers of q which are of the form q to the power 5k plus 3 or q to the power 5k, these are actually 0. So now we extract those terms which are of the form q to the power 5n plus 3, and then we find this identity. Okay, which is after rearrangement gives this, and which is after replacement q by minus q, we have this identity. Now we recall some relations of Ramanujan's general theta function and these Rogers-Ramanujan functions. So these are actually proved in earlier papers. So when we use this, when we plug these values of zq and hq in this identity, so this basically gives us this identity. So this is a new identity involving zq, zq2, zq3, zq6, and hq, hq2, hq3, hq6. Okay, so this is a new relation. But we want to prove that relation involving rq, rq2, rq3, rq6. Okay, so now we look for a companion of this relation. Okay, so for searching for a companion of this relation, what we do next? Next we set a equal to q and b equal to q square, and then using a similar analysis, we find that these powers of q in this power series are not of the form 5k plus 3 or 5k plus 4. Okay, so we now want to find the 5 dissections of this power series involving zq and hq. And similarly, we use Jacobi triple product identity, and then we express this power series in this phi of minus q3 and 1 by chi of minus q. So to find the five dissections of this, we may find the five dissection of this. Okay, but we already have a five dissections for phi q, and if we replace q by minus q3, then we get a five dissections of this phi of minus q3. But again, we don't have any already available five dissection for 1 by chi of minus q. Okay. So again, we go back to Ramanujan's notebooks. So in his second notebook, Ramanujan again wrote this identity, which involves psi square q5, phi of minus q5, and 1 by chi of minus q. So using this relation and these five dissections of psi of q, because here, since we wish to find the five dissections of 1 by chi of minus q, this is a power series of q to the power 5. This is a power series of q to the power 5. This is also a power series of q to the power 5. And so we plug here these five dissections of psi q, and then we do the necessary simplifications. And again, using this last part of this identity, we simplified these three terms to this single term. Okay, and hence we obtain this five dissections of 1 by chi of minus q. Okay, so to summarize, first we have observed that the powers of q in this expansion are not of the form 5k plus 3 or 5k plus 4. Then we have expressed this in terms of some product involving phi and 1 over chi. Then now we need to find five dissections of these two. Then using Ramanujan's identity, we have found the five dissections of 1 by phi of minus q and also for phi of minus q3. Okay. Now we multiply these two. Okay, so this is the final five dissections of this power series. And since the terms involving q to the power 5 n plus 3 are absent in that power series, so we extract those and equate to 0, which gives us this identity. And again, using these relations, known relations between f of ab and zq and hq, we obtain this new identity involving zq, zq2, zq3, hq, hq2, hq3, hq6. Okay. So this is our recently obtained identity, and this is the identity we obtained earlier. Okay. So these are two. When you look observe closely, that you will see that the right hand side of this is just the reciprocal of this with this extra factor of q, of course. And now here is some interesting thing to happen. So if we multiply these two things, the right hand side gets cancelled out, only q remains. And what happens to the left hand side? So now we multiply these two things, and we actually arrive at this. Okay. So when we multiply these two things, we see that all these terms in the left hand side becomes some functions of rq. Okay, so for these two, from these two we get these two things, and from these two we get these two things. Then we transfer these to the right hand side. So these are three new identities. This is these two are identity for involving zq and hq, and this is the identity involving rq, which actually comes from multiplying these three. And these three are new identities. The proofs of other identities that we have talked in this presentation, the proofs are actually quite different. Actually, they have been done using different approaches. Some has been done using the quintable product identity, and some has been reduced by using the previously available identities. Okay. So with this, we come to the end of this today's talk. So the contents of today's presentation. So this second thing, the identities for arousal summarization of continued fiction, this has been already published, and the first part, that idea, that the study on Lister gaps, this is still under review. Okay. So these are my other publications during my PhD, and these are some references related to these works. And finally, my sincere thanks to my supervisor, Professor Noyendip Dekaborua, and to the organizers, Fatnagar sir and Dixit sir, for giving me this opportunity to present my work. Yeah. So thank you. So now, if you have something to ask or discuss, then I think you can.
Thank you, Pranjal. Very
Yes,
nice
sir.
talk.
Thank you, sir.
Any questions and queries?
Yes, maybe I can ask a question. I enjoyed your talk very much. There are some so-called shifted identities and considered by Frank Garvin, I think also with co-authors, I think with Hamza Yesil-Yurt, which also are like three-term theta function identities. They can be considered like that. It might be that what you found is a special case of something there, but
Okay, sir.
I can maybe in one of your cases, but I
Okay,
can
okay.
try to find a reference. I can send you this.
Yeah, yes, sir. Yes, sir.
There's also a
Thank you, sir.
paper by Ladi called the quintuple product identity and shifted partition functions, published in 1996
Okay.
in the Journal of Computational Applied Mathematics. And here's a mod 6M identity, which is very general. And the M can be specialized to 5, and then you get your mod 30
Okay.
dissection, where you had two new identities.
Yes, yes.
It might be that there are some connection to other existing work, which is good for you to know.
Yeah, yeah.
Yeah. Also, have you tried Gurnitz-Gordon
Yes, sir.
continued
Actually,
fraction?
I'm thinking of working on this continued fraction also by
Mhm.
applying the same methods. But I have not yet started actually.
Okay, I see.
Okay,
Yes.
thank you.
So
Any
this
other
is joint.
comments?
This is joint work with your advisor. Is it your own work?
Yes, sir. Yes, sir. It is joint work with him.
Okay. So I
Yes.
can then send email to both of you then to Bibikanandi Mache. Is it correct, or is it
No,
Parua?
Barua.
Parua. Parua.
Yes.
Okay.
Yeah.
Okay, I see. So Parua he's attending the
No, Barua is
meeting.
not there.
Yeah, that's why I was surprised.
No, sir.
But
Actually,
okay.
he is busy in some other
Okay, I
things.
see.
Yeah.
No problem, no problem with
Sir, I can send you a mail, then you can send me the papers there.
yes, okay. I will
Yes,
do
sir.
That'll
that.
be good.
Yeah, yes.
Fine.
Okay. Any
Thank
other
you.
questions or queries?